mostly XMOS chips. Now I understand it. The situation is getting better. Now, well, let's start transputing again. So my talk is slightly difficult for the beginners, but I will try to explain more easily. Well, anyway, Epiphany chips consist of many cores, and which provides a shared memory and message passing architecture. But many to get a good performance, parallel programming based on both shared memory and message passing is a key feature. Why? This is the point. Currently, many users are using shared memory basis. So my talk is to fill this gap. This was a picture of the transputer. Transputer is the name of the microprocessor of parallel processing created by IMMOS in the UK about 1984. So it's mostly 30 years ago. When I looked at the architecture of Epiphany, it's very much like a transputer architecture. We are very excited about to work with the Epiphany chip. And the UK people are also looking at the trend of this chip or supporting parallel computing, programming languages to Epiphany chips. Why it is so exciting? I can tell you one of them. So, this was an exciting demonstration. You might know the left side is the ray tracing, the right side is Newton's cradle. Especially cradle was very realistic, dynamically, the ray tracing. This is very, good starting to know what is about the parallel computing. We tested over 100 transputers, and parallel computing really works. That was the first beginning of the parallel computing age. And we had also, one thing is very important. Sorry, this slide is broad because I copied this data from the dataset. Important thing is a number of transputers are listed at the left side and up to 80. But we actually tested it and connected up to 100. And the right side, the linearity, the increase is up to 95. This is amazing. Why is it? We should think about to port or to borrow this idea to Parallella. Very efficient work. There's a nice report, Jamie's technical note, still available in an internet access. You can download Jamie's technical paper. And IMMOS mandible set demonstration. This was also an amazing demo. 30 years ago, we had only IBM machine and Intel's 286. That was very slow. The one chip transmitter was over 20 or 30 times faster than that. The once small area is determined and then compute the results very quickly. Another interesting thing is interaction of parallel computing to mechanical devices or networking or any types of I/O. This flight similarity is, well, just imagine that there are 4 PCs are provided, and each PC has a transputer plug-in card. So each transputer card can communicate to 1, 2, 3, 4 different PCs. And each transputer has a communication links. That link is magic. Each PC can communicate, which means that one object in one PC can communicate to other PC. This means then object, in this case, that's airplane, object flight over the PC via synchronization. So airplane can fly over any places of the PCs. This is one good difference to Parallella, because Parallella is supporting communication mechanism. This is another demonstration. 100C is very much like similar to Occam. This is a programming language, and once 100C code is compiled, that code is mapped to FPGA gate level, I mean cell level. So software can run in hardware. In this demonstration, just to number plate is captured. Once one number plate is captured, then this number is tracked while the car is running. So in this case, the number of processes are probably more than kilo or 10 kilo. So more than kilo cores are running in parallel with the communication. Very amazing software. So the communication and the concurrency is very useful, especially embedded applications. Now, coming back to Epiphany chip, you know what it's about. If you look at this picture, this is very much like a transputer. The routers, the microprocessors, are just sending message to any places. So this communication can take place. So ask Andreas, what is the idea comes from? Is that correct? All right. This was 1991. This architecture is commonly used in network on chip as a Carré chip in France and Parallella, and many other chips are using this architecture. Very network-centric architecture. Textbook, everything is written. The ideas of routing, ideas of networking. If you are interested, this PDF file is still available in the network. You should read it. Okay. It's program models in a different manner. It's written many ideas. It's a collection of everything, collections of everything. But at last, stages. There are message passing and communication, communicating sequence processes, CSP. Other CSP is a mathematical process algebra. Well, this idea is very much suitable to adapt this architecture. Oh, it's the same thing. Distributed routing technology or inter-core message passing sort of thing. These things are fundamental concept in Epiphany. But looking at so many programming languages supported, mostly OpenCL, OpenMPI, Go, Erlang, Python, and C program. Go or Erlang is a subset of a CSP model, and an OpenMPI is looks like a CSP model, but it supports only on the interfaces. It supports the interface of input data or output data. That's very weak for supporting process model. I mean, or else. You might know that the guideline as a computing model is a task parallel and data parallel. This is okay. But the CSP model covers much more. Much more. What is about CSP model? We're just adding several constructs. One is a parallel. And message passing. And then an additional feature is mobile. Mobile is a new technology, especially targeted to ubiquitous computing, which Andres mentioned. So everything, very complex model of parallel computing. Model is embedded within single programming language called Occam or OccamPi. So simply using this programming language, the application tends to be more enjoyable, like this. The circle is just represents a process, and arrow is indicating the path of message passing. And process can be hierarchically constructed, so very complicated process can be interpreted using a single Occam or OccamPi. Another feature is barrier functions. This is also useful to synchronize with the time. It's Parallella architecture. This is the Epiphany chip, having E-link applications. You might want to send data from this chip to or motherboard, or vice versa. You need some communications scheme. When applying a Parallella to specific applications, using IO-Pi, this is a new word. IO-Pi means input, output runs in parallel. This scheme is very, very useful for embedded use. So just imagine that. One example. and in this case, image is sending to the printer, as printer is trying to print out the data. And using a conventional programming language, you need 3 stages. So looking at from a printer side, so printer need to receive the data and compute something, and output the data to the printout. So 3 stages are needed. But using I/O PAR, input output can be overlapped. So it's very fast to handle with printing processes. The program code is something like this. I don't want to explain one by one, but the idea is while receiving the data, you can get another data, and when receive first data, you can pass it to another process, and you can repeat the data and pass it using a pipeline structures. So input output can be cancelled out. So computing time reduces very, very quickly. How can we write it? This is the sort of code using a conventional code. It's impossible. It's impossible. So, well, probably all the Parallella might be connected to robotics application, or control mechanical control, or networking. This idea is very efficient. While computing, you can receive data, and process it out. 3 stages are running in parallel using 16 or 64 cores. How can we do it? Oh, sorry, coming back to it. Yes, that one more thing. Yeah. My target is to port CSP Occam model to Parallella. It's a compiler called OccamPy. Is available from UK site, University of Kent. And Transputer is, we call it a Transputer virtual machine. Using a subversion, you can rebuild Transputer code to ARM chip or any kind of a microprocessor. Well, this can be used in a Raspberry Pi. So try to run the Parallella. And then JCSP is a CSP library for Java. This is also possible to port Parallella. This is the C proper version. And also Python CSP is available. Many people are using OpenCL, and OpenCL can access C proper. So this is a good candidate to port. So everybody might be happy. The one evidence is OccamPy was ported at Halmstad University of Sweden. It's very exciting. So it's probably hybrid model of combining shared memory and message passing is right way for the Parallella. The hybrid model parallel computing is a big trend of industry and academia. Actually, all-time GPU, the CUDA, is supporting message by MPI, message passing interface library. So why not doing with Parallella? Just mixing together. So computing might be much more fun. Expected silicon modification, as many people are craving, 32 kilobyte of memory is not enough. We need more. The other issue is we need to support something in network configurations. To connect a mesh torus or to change mesh torus, butterfly, hypercube, cross. Especially cross network is useful for embedded use. If you are interested, just read this textbook. Answer is here. My conclusion is as Epiphany chip architecture is similar to Transputer, a process model is proposed to increase performance. Hopefully you understand this one. Any questions? No? Hi. How many memory? I haven't tested. Transputed. 255 and megabyte. Yeah, 1 megabyte or 2 megabytes more. Real time, this change here. What do you think about? Well, memory size, your roadmap is saying something going better way. It's a big issue. But think about it. Any questions? Nothing. Okay. Thank you very much.
Thank you. ありがとうございました。じゃあ次のセッションの